All right, so we'll finish up the review with going through an independent samples t-test example. So again, this is one of the most common statistical tests you're going to see in just about any given research paper, especially those involving human subjects research, like those you'll see in psychology, sociology, a lot of public health stuff as well. So the key component of these independent samples t-tests is that we have two samples. And so when we look at our formula here, and here's where you need to find everything, what we are primarily interested in is usually always denoted in the numerator. So here in the numerator, we're looking at the difference between the mean of two completely different samples. So the mean of sample 1 minus the mean of sample 2. Again, here the order doesn't matter. We just want to know about the difference between the means of two completely separate groups. So that is no big deal. You can find that pretty easily. You can get the mean of one group and the mean of another group on any given measurement. The more difficult part about an independent samples t-test is that denominator. Again, the denominator, the whole thing is considered the standard error. But specifically within here, you see the variance sub p. So s squared sub p, that is the pooled variance. And there was a question and a request about this for topics to cover on this review. And the pooled variance here is really just a weighted average of the variance. The reason why we have to do this is because we have two completely different samples. So when we have two distributions, not only are we having to account for the means of each distribution, but we really also have to account for the variance of each separate distribution. So again, this is just all goes because we have two samples that are independent of one another, so we have to have what's called this pooled variance. And really, the pooled variance is where you're going to spend the majority of your time in any calculations for an independent samples t-test. So let's do a quick example using just a few numbers. So let's say that there's professors, they want to know if there's a difference between two sections of a PY216 class on their exam 1 scores. So they're going to take 4 students from one section and compare them to 4 students from another section. So we have two, get a different pen color going. So we have two samples, the people from section 1 and the people from section 2. These are all exam 1 scores. So this represents X bar 1 and X bar 2. And again, this part's really easy. You can get the mean for section 1 scores and the mean for section 2 scores. No big deal. The difficult part again is going to come from the pooled variance. So again, essentially what you're doing is, because you have to account for the variance from sample 1 and the variance from sample 2, pooled variance just means let's account for both of them at once, and that's what's going on in this formula. So as you can see, a lot of this stuff is easy to get. N sub 1 is just the people in sample 1, N sub 2, the people in sample 2, and here you see variance for sample 1 and the variance for sample 2. So independent samples t-test, the reason why they seem more complex is just because the steps take longer, and that's all because of this pooled variance. So this is the variance from sample 1. Here's sample 2's variance. So you're having to get the variance twice, once for each sample. And the pooled variance just puts them together in a fair way. Now, there are other formulas out there for if you have equal numbers in each group, which we have in this case. But the formula that you see here will work no matter whether you have equal numbers in each group or unequal numbers in each group. So this is your safest formula. So keep in mind that this is not the standard deviation. When we have been doing the the single sample t-test and the dependent samples t-test, you've gotten a standard deviation, and that has gone into calculating that denominator, the standard error. We are not getting standard deviation here. We're getting variance for each sample. So make sure that you calculate variance for each sample and you don't go that extra step where you take the square root of the variance. You get the variance, and that's all you need from each sample. So let's break this down and do the variance for section 1, or our first sample. So we have the all the values for section 1, and if we get the mean of them, I'm going to call that X bar for section 1. The mean scores for section 1 was, let's see, mean scores for section 1 is 88.75. So going to do everything just like we have been and get the difference between our values for sample 1 and the mean for sample 1. And it's going to give me a new column, which I'm going to call X minus X bar 1. Again, my footnote of 1 just means section 1 or sample 1. If I added those up, I get 0, so that's useless to me. So again, I want these values squared. So if we square them, and then we add them up. Again, this is all because the formula for variance so we have the numerator here. And here we have n minus 1, so we have 4 people in section 1. It's going to reduce down to 4 minus 1. So the variance for section 1, 8.92. And we stop there. We don't need the standard deviation. So now we're just going to do the same thing. Now we're going to do it for section 2. So the mean for section 2 here is 75.5. So we will do the exact same steps just for section 2 using their specific data. And I realize there's a lot of different ways of writing out your problems. I do recommend, even though this seems very, very tedious and almost dumbed down, doing it in this very slow stepwise manner helps you keep things aligned, because when we move forward into some more complex calculations, you will need to be very careful about keeping things in line and understanding where what comes from what. So get in the habit of being very tedious with these calculations. That's my recommendation to you, and that is free. Okay, so now we want the differences between our values and the mean for section 2. Again, that's going to give us a value of 0, so that's useless. So we want to square this. So if we add those up, 217 even. So again, that's the numerator here for our formula for variance. So again, we still have 4 people in section 2. So our variance for section 2 here is going to be that numerator we just got, 4 minus 1, and that's going to give us a value of 72.3. So this is our variance. We don't get standard deviation. We don't need it. We stop there. So now we have everything we need to calculate the pooled variance. So if we write it out now, by the way, this P here just stands for pooled, if you didn't already figure that one out. So n minus 1 is the number of people from section 1, that's 4. We just got variance for section 1 earlier. We had 4 people in section 2, and the variance for people in section 2, that was what we just got, which was 72.3. And of course, just the same as it is in the numerator, these sections still have the same people. So when we put that all together, this is our pooled variance. Or variance pooled. So now we have everything we need. So earlier when we were calculating variance for each section, we got the mean for each section. And then we have the pooled variance, which you see is used in the denominator of this equation. So let's plug in everything. So notice this is basically pooled variance divided by section 1 individuals, pooled variance divided by section 2 individuals. So those values are going to be the same because we have the same number of people in each section. But this is especially important to keep them separated like this if you have unequal numbers in each section. So if I had a class full of 5 versus a class full of 3, this formula would make a whole lot more of a difference, and really important to keep them separated. You can't go wrong with this formula. There are reductions you can do and simplifications you can use if you have equal numbers in each group. But my recommendation is that you just go with this formula because it will never serve you wrong whether or not you have equal numbers in each group. So pooled variance, we just calculated. It's the same for each group. So that is somewhat of a handful to write, as you can see. So just a bit of a simplification, reducing it here. Alright, so now we're pretty close. And there's our t-value, 2.94. Alright, so we go back to our table, and if you remember, were we doing a one-tailed or a two-tailed test? You need to go all the way back to the beginning and make sure that we're clear on our wording. We wanted to know about a difference. We don't see any mention of direction, no greater than, no less than. We're just looking for a difference. So that means we're talking about a two-tailed test. Let's move through everything. Here we go. So we want a two-tailed test, 0.05 level. Now, this is where things are going to differ a little. DF for two independent samples is going to change it up a little bit. It's going to be n plus n minus 2. The reason why, or another way you can think of it is, let's see, the best way to word that is to say n minus 1 per sample. So n minus 1 for sample 1, n minus 2 for sample 2. This is the same thing of just saying let's add both sample numbers together and subtract 2. So that's how we get to this. So we had 4 in section 1 plus 4 in section 2 minus 2. So we're subtracting 1 from each sample. That'll give us a degrees of freedom of 6. So if we then need to locate where that point is, .447. So again, we are comparing our value to the critical value, and our obtained t is larger than the critical value, so we reject the null hypothesis. So in plain language, that's saying there is a significant difference between section 1 and section 2 on exam 1 scores. And then the way we'd write that out in that general formula, and its relation greater than or less than 0.05. We have 6 degrees of freedom. Our t value is 2.94, the one that we calculated, and that was larger than the critical value, so p less than 0.05.